Daniel holds a PhD in computer science from the University of California at Berkeley, advised by John Canny and Ken Goldberg. He received his BA in math and computer science from Williams College. Daniel's research has been supported by a 6-year graduate fellowship for STEM diversity and by a 2-year Berkeley fellowship. He is the recipient of the Honorable Mention for Best Paper Award at UAI 2017, the 2019 Eugene L. Lawler Prize from the Berkeley EECS department, and was selected to be an RSS 2022 pioneer. So I'm really looking forward to this talk because Daniel has done some really impressive work on deformable object manipulation, as is evident from the title itself, whether it's cables, fabrics, bags, and liquids. So with that, Daniel, over to you. Thank you. Yeah. One slight thing, when you are free to ask questions at any time during the talk, but when you have questions, please raise your hand, and then Susan will be interpreting the question for Daniel.
Yeah, and the talk will have natural pauses as well. So I'll split into several parts, which you'll see. Yeah, so and just let me know if my audio isn't clear or if I have to do anything. But otherwise, yeah, thank you very much for having me here, and I'm really excited to be presenting about this. So, but many of us know there's been a lot of recent exciting progress in robot learning for manipulation, as exemplified by many of the exciting pioneering work. From my view, what I am really interested in is trying to advance deformable object manipulation, specifically for highly precise deformable, like with many of the examples shown in this slide. But why is this challenging? So there's a few canonical challenges that I like to talk about. So number one, it's difficult to represent and estimate the state of an object or where it is in the 3D world. So if you imagine this rigid block, if we know the pose of a particular point on that block, then we know its arrangement, the full arrangement in 3D. But if we have a tangled web of cable, then that's not the case anymore. You can fix the point while other parts vary a lot. Another challenge is how to reason about dynamics. So, sorry, some lag. Yeah, so how to reason about dynamics here. So if you imagine the image of a fabric and a pick and place action, which is from a real research project that I'll be talking about later, it's hard to specify what is the fabric going to look like after this action. And then there are issues with severe self-occlusion. So what I'm hoping to pitch to you today are different ways that we can try to address some of the challenges using both machine learning and learning good representation. So what do we mean by representation in robot manipulation? That's a bit of an overloaded term here. So by representation, what we really mean are we consider how we process, use, and reason about observation and action. So typically we'll have some kind of robot policy with some input and some output. Different observation representation include things like your standard color or depth images. We can have a segmentation map. We have some segmentation map where it shows a different shade of gray for each object. Then we have things like point cloud and key point, which are other types of observation representations. And then there's action representation, like, are we going to do 3D continuous control? Like if we're trying to control this ladle. And if we do that, then especially what is the rotation representation? Do we use Quaternion or Euler angle? No, we don't use Euler angle. If we're dealing with 2D tabletop manipulation, like moving fabric, then like how do we pick the picking point or placing? Do you explicitly predict something, or do you predict a value distribution over different picks? So this is the kind of diagram that I'll be and theme that I'll be returning to throughout this talk. So any quick question before we move on to the three major projects that I'll be talking about? And is the Zoom setup okay?
Yeah, I'm trying to check something, but everything is fine. But I'm checking about the closed captioning. Please go ahead. Yeah.
Okay. So let's just dive into the first batch of research projects. So here are the problem statements. It's fairly straightforward. Given some wrinkled fabric, figure out how to smooth it. And one way that we can do this is by, at least in this project, we do privileged imitation learning from a smoothing demonstrator. So as part of this project, we built our own fabric simulator, and then we used this algorithm known as DAgger to train fabric smoothing policy. And the reason why we can do that is because of the fact that we have a simulator, and therefore we can control like the ground truth. We can extract ground truth information. So concretely, we'll have some student policies. That policy is the thing that we're trying to train. And it will only take in like the image observational data, like color and depth. But because we control the simulator, we can, each time it takes an action, we can pass that information to the teacher, which uses the ground truth information from the underlying clock mesh. And then it tells the student what it should have done at that state. Like for example, it was doing a pick and place in the wrong direction. It should have been going to the like upper diagonal. And so with this process, we can then have this cycle where the teacher provides corrected label to a student. So yeah, using this general method, we benchmark in simulation a number of fabric smoothing methods from different starting configurations of cloth. We split them up based on tiers. And you can't quite see it here, but the tiers are arranged like left to right. So at the beginning, we have a baseline policy of just randomly applying pick and place. The resulting coverage should be very bad. We also have another baseline that involves, first taking the highest point of the fabric and then trying to pull it to the target. Another one, which is a very interesting one, is using a wrinkle baseline. So it's from this paper from 2013. So this was back before deep learning invaded robotics community. So it's a very interesting baseline where you have this wrinkle detector, and then we pull the direction perpendicular to the largest wrinkle. So that one does pretty well, although our method does the best and does the better. It's better on harder starting configuration in the third batch of results here. And if you're wondering about the starting coverage and then the demonstrator coverage, like that, the starting coverage is like the coverage of the fabric at the beginning when it's all wrinkled up. And so we want to be able to maximize that with the policy. So this is all in simulation, but ultimately we really care about getting this working in the real world. So we do a lot of domain randomization to randomize different parameters in simulation. And then in the real world, we can use the surgical robot and we do a bunch of picking and placing action and we're able to get a reasonably high coverage in the physical experiments. So this paper, this was about training a smoothing specialist. So this raises the question of, how do we do it for other tasks like folding or other manipulation tasks? So if we try to use the same method, we're going to have to retrain for folding and other tasks and then re-implement a supervisor. So a more general way of doing this is to try to train a single goal condition fabric manipulation policy that if you're given just some arbitrary starting configuration with some goal image, then hopefully the policy can just manipulate the fabric towards that goal. Yeah, question.
Could you speak more about the policy architectures and what the output actions are? Are they to move your end effector and then grab and so on?
Yeah. So for this paper and the prior one, we're just outputting like the 2D picking point and 2D placement point. So like that image and then it's an explicit architecture. So that's the same thing that happens here. And yeah, so how do we do this? So to this end, we're going to propose a method that we call Visuospatial Foresight. So it consists of two major steps. We first train a pixel dynamics model on RGBD data. So we use the same simulator that we developed from the prior paper, and we run like a random data collection policy and simulation. We get a lot of data. From there, we can train a pixel dynamics model. Well, we can train a pixel dynamics model that encodes the image, concatenates the action, and then it produces the predicted next image. And we supervise that with the self-supervised label of the next image that we encountered when we were collecting data. And again, this is all in simulation, but in order to get this working in the real world, we do have to do domain randomization. And the key is just making sure that within a single episode, we use the same randomization parameters. Otherwise, we'd have to predict random stuff. Yeah, so this is the dynamics model. Then in order to actually take action, we will then have to figure out a plan over it. So a plan will mean that we have some current image, we have some goal image. We do need to consider some kind of cost function, which is how far is the current image from the goal image. So we can use something like Euclidean cost function. And then we can use cross entropy method, so that involves sampling a bunch of action sequences. We rank them according to the cost function, as you see here, and we're using the pixel dynamics model from the first step in order to generate the prediction. And then each of these rows is a single sample action sequence. And then we use cross entropy method to refit a multivariate Gaussian distribution. And then we repeat the process. So it is a standard sampling procedure for figuring out a good action, or generally to approximate the minimum of a function. Yeah, then we take the first step, we discard the remaining action, and then we repeat the process. Yeah, then here's some results in the simulation, and we can do this kind of picking and placing action in them, and then we compare the smoothing performance with the prior paper, which was specialized for smoothing, and we got very similar performance, which is good because our policy can also do things like do double fold and triangular fold, and it can do some stuff in the real world. So this is a Da Vinci surgical robot that we have in our lab, which we've been using for a lot of our fabric smoothing work. And yeah, the action magnitudes are limited because we limited them in training, because otherwise it would generate very big pixel changes. So that's one of the considerations that we have when we're working on it. Yeah, question?
Yeah, so is the cost function just pixel-wise difference of the image values?
Yeah, pixel is the Euclidean distance between the current image and the target image. There are other ways that you could define distance function. We explored quite a few, but they ended up not working as well. And
okay.
Euclidean is very easy to describe to people.
Okay.
Yeah, so what are some takeaways? So yeah, we can do fabric smoothing and folding using image data. And from a representation perspective, using images is pretty straightforward here, because otherwise, if we try to approximate the fabric with a finite set of poses, it's unclear how do you do that with a fabric. But I want to take a step back and think about what is the action representation, because we used something that was somewhat straightforward, or we were basically either explicitly predicting a picking or placing, or we were using a sampling-based procedure to do this. So we covered, so like this is the way that we configured it so far, but yeah, the next major project, I'm actually going to present also like tabletop manipulation, but with a different action representation. So does anyone have any questions before we move on to the next project? Yeah.
Yeah, so in your training, you are taking pictures from a very specific angle. You're taking pictures from overhead, and I was wondering if the position of the camera changed, would you have to retrain? And what would that retraining process?
Yeah, well for this, for standard, like the top down manipulation, we typically have the camera top down, and so that makes it a little bit easier. But to transfer it to real, because in a real setting we have to place the camera somewhere, and then there's always going to be human error, and then maybe some like undergrad bumping into camera, so the camera angle will sometimes vary. So if you randomize those parameters in simulation training, usually it will probably cover the distribution of what the camera angle might look like in real. Other than ways that we can address it, I'm not saying it's 100% bulletproof, but it's just a way that we can. Yeah, question.
For your fabric smoothing task, it looked like you were assuming a square fabric. So with other shapes of fabric, did you ever try that? Because it seems like the wrinkle method would generalize better.
Yeah. So we did do squares here. We generalized to some. I didn't show it in detail, but there are some different types of slightly different types of fabric. But yeah, we were using squares. But I think roughly, these methods don't necessarily assume a fixed shape of. Like we can use the same method, but assume like a different distribution of shape of fabric. All right, so maybe we can move on to the next major project. So here we're going to switch to talking about some project that has some novel action representation. So here we're going to again consider like 2D manipulation. I call it tabletop rearrangement. So this is all in like a Pybolix simulator. It's a bunch of tasks that we designed in simulation to partially open source it so that other researchers could try to build upon it to accelerate progress in the field, to facilitate comparison among methods. So yeah, this is a set of simulated tasks, and the question that we want to pitch is, if we have demonstration on how to do the task, then what is the action representation? I'm going to get to first discuss like how the demonstration looks like, and then we'll talk about the action representation. So each of these tasks will have some kind of scripted demonstrator. So in this example, we will have a task that involves manipulating a cable toward the target. So in this example, the demonstrator will keep doing picking and placing action in order to match the cable to the goal. And these are the top-down images plus the goal image. And so a single like data point is going to be the current image, the action, and then the fixed goal image. And one of the novelties of the simulator is trying to pitch some new task that involves some kind of bag or more generally item containment. So in this example, we were able to program this robot to try to open up the simulated bag so then it could contain the item. Oh. Sorry, I'm lag. Yeah. So this is like the form of the demonstration data that we have. So we have a lot of tasks, demonstration data from a scripted demonstrator, and then we want to train a policy to imitate this. from demonstration so that at test time and we sample the same object but in different starting configuration. How do we do that in a sample efficient way? So that's where the transporter network comes in. So let's first review what the normal transporter does, because that's a very impactful paper from a few years back, and then we'll discuss what we did, what changes we did on top of this. So transporters they're a neural network architecture that's very well suited for the kind of picking and placing in a 2D setting. So it consists of two main steps. So it consists of localizing some region and then inferring how did that region displace. So that can be thought of as picking and placing. And the localized region can be like the entire object, part of the object, or multiple objects. So a naive way of trying to infer the spatial displacement is by predicting two values, a change in x and a change in y. But that's not what we do here. So the transporter will do something clever. So this visual is just showing some deep visual features that are like outputs of networks. And then we do a crop, well, we do a sliding window operation, which is just like a convolution does in 2D. So at least that's the way I literally think of it and how I implement it in code. And by doing this, it does a brute force math searching over all possible placement points with the highest value indicating the placement spot. So if you're wondering, like, why are we talking about transporters here? The reason has to do with the theme of representation. So there are three concepts here: the use of orthographic images, the notion of equivariance, and the use of fully convolutional networks. These together explain some of the representation advantages of transporters. So an orthographic image means that each image contains the same like fixed block of 3D space. So it's not a perspective image that will have distortion near the border. And by using fully convolutional network to map from input to output, where it will output a distribution over picking and placing, if we shift the input by some amount, then the output should also shift by some amount. And so the network doesn't have to spend extra capacity trying to learn this thing. Furthermore, there's also the notion that many times in picking and placing, our distributions are not unimodal. And sometimes they're not even Gaussian. So in this case, it would be okay to pick any point on the L-shaped block to place it. But that L-shaped block is not a Gaussian distribution. And how do you specify it? You can specify it by specifying a distribution using an image where we interpret the image as a probability distribution over each pixel. Yeah, so those are some of the representation advantages of transporters. But there's a limitation in that it only takes in some current image. And if we supply different target images, then how do we do that? And again, this is important for Deformable because it would be hard to specify a target as here are here's a fixed set of finite poses for the target. So that's why using imagers as with the prior paper is useful for Deformable. Yeah, so in this example, the goal is to try to put the block into one of the bags. So this one is the yellow bag. And this is what the architecture looks like that we developed. So there's a lot of things to process here, but we'll walk through the forward path. So first, a naive way of trying to use the goal image is just to stack it with the current image and then proceed with normal transport. You can do that, and we tried that, but a slightly better way to do it is to split the processing a little bit. So here's how it works. Our current image is passed through 3 fully convolutional networks. So all 4 of these are fully convolutional neural networks that will take in some image and output an image of the same dimension as the input. Yeah, so we pass it through what we call picking, query, and key network. So the terms query and key, we just borrow them from databases. Like they don't really mean much here. So with the goal image, we can pass it again through the picking network, but also through a separate goal image. So the result of this is that the picking network will produce a heat map over the possible picking point. Learn from demonstration. The separate goal image will process the goal feature. We call them logic here, but they're basically just think of them as features which are outputs of network. And then we have to do this thing, which we're going to use element-wise multiplication on a per pixel basis to propagate the goal information to the query and the key information. Yeah, question?
I may have missed this, but are you using a standardized filter for your query and key convolutional networks? Like, what kind of filter are you using?
So by filter, are you talking about like the weight of the convolutional neural network? Yeah, these are just off-the-shelf residual networks that have 43 layers.
Oh, okay.
Yeah. Or we can all, the exact architecture doesn't really matter too much as long as it's deep enough and it can fit into your GPU.
Yeah.
Yeah, and then like at this point, we're at the final stage of the transported architecture. So we make a local crop at the picking point, and this sliding window operation is again a convolution. So like this is literally the animation that I think of when I think of like how does architecture work. And this will then tell us the placement plot. And we can learn all this from demonstration. And as I'll show later, it's very sample efficient. So here are some examples of this thing at test time. So we tried some chat that involved, you put some things in A, then you put them in a target. And you're actually able to do this in Python, even though there's like obvious limitations to the thing later. We can vary the goal at test time. So in this example, the joining cables are all in the same configuration. And then the policy will be able to match the goal, but in these examples, the goals are different, but this is all the same policy. And starting from the same configuration, but we just apply, here's a different image, move the cable there. And quantitatively, we'll show some results with learning from one demonstration and 10 demonstrations. So one demonstration is just like, one example of that pick and place, maybe 2 or 3 actions in one episode, but it's just one demonstration. We have 4 different tasks in our benchmark that are goal conditions. So they're visualized here. So a naive baseline, or at least a baseline that makes sense is instead of using imagery, let's just get poses. And then we'll take these poses and feed them through a multi-layer perceptron to directly get the action. And it uses ground truth information from the simulator. So we're just going to assume that we'll just provide it to the baseline constraint. And if the success rate at test time is not that great, especially with one demonstration, and on average, the transporter approach works better. Sorry, I'm lag here. Yeah, there we go. Oh, yeah, question?
Yeah, so I think before you began talking about the transporter, you mentioned something about novel action representation. I was wondering, like looking at the transformer, it seems like that's trying to solve the problem of, being able to specify how to manipulate an object from point A to point B, how to pick and place it from point A to point B. But the the actions, are they still pick and place actions in this scenario?
Yeah, the actions are still pick and place.
Okay.
It's just that the way that we choose the action is different. It's by taking the crop and then doing a search over all possible placing points. But that searching process is very efficient because it's a convolution. So it's sort of like there's an equivalent between the brute force search and the convolution operator. And that's something that I find really interesting from a representation perspective. We're effectively searching over all possible, taking place by searching over all possible ways of displacing a crop.
Yeah. So then a follow-up. So is it any different from, say, something like DexNet, where when you try to find out physical? Oh, DexNet.
You mean DexNet from
Yeah.
Ken Goldberg?
Yes. Yeah. Where when you're searching for grass, given a scene, you're trying to figure out what are good grass locations. That too is a brute force search that you turn that into a CNN like operation.
Well, yeah. So first, it depends on which version of DexNet we're talking about. Like, I'm not. They have like 5 different versions, and there's a lot of different variations, but none of them, to my knowledge, use the transporter approach. Although they will, like, there are some approaches that do like cross-entropy method to find a good graphic point. There is one paper that uses fully convolutional network to get a value distribution over pixels. That's probably the closest one, but it doesn't really. So with DexNet, there's not much of a concern over picking and placing. It's mostly grafting. So so it's a bit of a different problem statement. Like it's picking but not picking and placing. Yeah, good question. Yeah, and to quickly recap, like why are transporters a good? Question.
Really cool result. I guess I have one question regarding the goal image. It seems like the goal image does not really represent what might happen within like intermediate action.
It doesn't do that. Yeah.
So how does it? Because I saw one demonstration where it's able to pick a block, put it in a bag, and then put a bag at a spot where the final image seems to not have shown the block in the bag. How is it able to do that?
So, well, some of the bag manipulation tabs, they're not goal conditioned. So in this benchmark, we have both goal condition and non-goal condition. So some of them don't involve the goal, but some of them I think the example you're thinking of is the one where we show the model architecture, and it's a little hard to see, but it showed the item like in there. It's a little bit hard to see. But it's in there.
Okay.
All right, so maybe I'm going to speed. I have to wait for the animation to come. But we can see the forward path again. And yeah, I have about 15 minutes left, so.
Yeah, maybe for the sake of time, let's keep the rest of the questions to the end.
Okay. Yeah, so these are the results that we have, and then we've already covered like the first 3 representation of damage. But what I find interesting is that we are using rigid displacement, but we're applying it to deformable rearrangement. And somehow that actually works because it seems like we have. I don't know if with rigid displacement, I didn't know if it would work for deformable, but in practice, it actually does do a little bit. It does pretty well. That's an interesting thought exercise. And the goal condition one will retain the representation advantages of the normal transport. But here are some limitations. I really like showing this animation here because it shows the limitation of this tabletop picking and placing. So fortunately, in the next major project, we're actually going to cover a project that tried to tackle both of these limitations. But then we're upgrading from like 2D to 3D manipulation. So now here we're going to be learning from point cloud. So a point cloud is a different observation representation. It involves like a set of endpoints, each with dimension d, and there's a number of advantages for why we might want to learn from point cloud. So here we're going to talk about something called ToolFlow. So what is ToolFlow? Under the assumption that the agent controls a rigid tool for 6-dot manipulation, then ToolFlow is going to be defined as dense per point vectors that show where each point on the tool moves in 3D space from applying the flow. Here's an example. We're controlling the cup of water. If we're just moving it upward, the flow vectors are all pointing up. If we're rotating it, then the flow vector should show that, vectors far away from the center of rotation should be longer. Now, this is showing a single rotation along an axis. And yeah, here are some examples of environments that we tested in simulation to help debug and develop the method where we have color image, a point cloud where we segmented it, so there's different colors meaning different things, and then the ground truth tool. So like visually, like that's how I think of flow. And here's a scooping example. So here we don't have the water in the point cloud, but here we're controlling from some kind of tool. And yeah, the original motivation of this was we wanted to do assistive feeding where we control a tool. And so we developed this test task to investigate.
Just a quick clarification question. Sorry, I am not following my own rules. But what is this simulator you are using for this?
Oh, it's NVIDIA Flex.
Okay, got it.
Yeah.
Nice.
So here we're going to assuming we have demonstration. How do we learn? And that's where we introduce ToolFlowNet. So this is our like novel architectural contribution in this paper. So the input is a segmented point cloud. The backbone is a so-called segmentation point net plus. Now to clarify, we're not doing a segmentation problem. We're only using a segmentation point net plus because it gives a per point output. So if we have like 100 points as input, we get 100 different outputs. And if we assume that the input is segmented, we can extract just the flow vectors that are the tool points. So yeah, that's the backbone. And the last layer, something. Yeah, there we go. The last layer is a differentiable singular value decomposition layer. So it has no parameters, but it does an SVD procedure. And you can actually do that in a fully differentiable way. So you can call the layer, you get a transformation, and then you can backpropagate through that layer. And the reason why, if this is like surprising, why is the SVD coming in? The reason is that SVD, if you give it 2-point cloud, you can use that layer to figure out what transformation will best align those two 2-point clouds in a mean square error effect. So think of a value decomposition as a very broadly applicable method. And fortunately, it ended up working here because we have a rigid tool, so we can reduce all the poses to all the flow vectors to like one token. So yeah, this is the architecture that we are pitching. How do we train? So before SVD, we'll have like per point flow prediction. Maybe they're a little bit noisy. We have this differentiable SVD, and then we can get the transformation, and then we get the induced flow from that. And we have ground truth ToolFlow. We can extract that from demonstration if we assume the point cloud and the action. So you don't have to assume like one-to-one correspondences, although you can do that if you want. So the loss function will be like a point matching loss function among the predicted flow of the predicted point and the ground truth at the next point. And that's good because we don't have to do something like, here's the rotation loss, here's the translation loss, try to balance those two. Like both of them are put together in this point matching loss. And then there's really key loss that we found is really helpful, a consistency loss. So this means it's based on the intuition that if you have 2 points that are close to each other, their predicted flow should be in some sense consistent. That's why we named this a layer. And so this is like an internal regularizer that we weigh a little less than the point matching loss, but we found it very helpful. Yeah, and then we have some results from learning from a set of simulated demonstration with full 6-dot manipulation. Here are some examples. And if we combine the results together, we tested a number of different methods. So that involves things like just using what we call a classification PointNet++ to directly get the output. We can use a segmentation PointNet++ to get an output from one of the outputs. And then we have a whole bunch of methods with images. We're using convolutional neural networks with depth images, color images, and segmentation maps too. And yeah, we found that on average, across the different environment, the ToolFlowNet ends up with the highest performance on average. So so one thing we were wondering about is when is ToolFlowNet helpful? And we believe that it has to do with the difficulty of representing rotation. We tried a simple, to investigate this question, we tried a simple 3-dot translation only example, and we found that the performance of ToolFlowNet with a naive baseline was very similar. But if we just artificially introduce this rotation, then ToolFlowNet gets a lot better. And the normalized performance is above 1, since the demonstrator actually doesn't do that well. We divide it by the demonstrator performance. Yeah, so we're not claiming that this is the way to do 6-dot tool manipulation. Just we believe that it's all vectors might be an easier representation to learn for rotation compared to other like axis angle, oil angle, and this interesting paper on 6D rotation like that. And this is all in simulation, but we're hoping to get this working in the physical experiment. So we do have some learning from like translation data where we attach a ladle to the end effector of a foyer, and we're able to do this kind of scooping motion. And we're also working on getting this working with the rotation as well. All right, so in the limited time left, I'll just cover some very quick takeaways plus the brief sampling of some ongoing project and feature work ideas. So we talked about the theme of representation learning, like what's the input, what's the output. We covered, using fabric. We covered, using different action representation for tabletop manipulation and tool manipulation. But there's other types of like observational representation you can use for fabrics, especially. So one of them is using dense visual correspondences. So that's another representation where the key is if we have 2 different images of fabric, if we know a point on one image, what's the corresponding point on the other image? And that can help generalize actions across different images. And for those of you attending IROS, we have a paper on ignoring images and using tactile information to simulate different layers of fabric. Other ongoing and recent projects include action representation, but for more dynamic motion. So we have things like tossing fixed endpoint cables, free endpoint cables, and pointing fabric. So the key takeaway that I hope that you get from this is that we can define the action of parabolic motion and reduce the learning to learning like the waypoint of that motion. So that makes the learning problem simpler than trying to learn like every single movement in 3D space. And just two very quick summaries of ongoing and future work projects. So I really want to get back to working with physical bags. So my prior work was mostly remote because I was working remotely, but in the physical world, manipulating bags like looks something like this. And this is like wonderfully complex. Like if you have to think about high deformability, object relationship, and the issue of relationships, I feel like is getting more attention in the research community. I hope it does. And we have an initial step in this direction where we're working on like more quasi-static dial manipulation. But I'm hoping to do more closed loop work in right now or in the near future. And the second, the last thing I wanted to talk about was manipulating plant. So I'm really getting excited about agricultural robotics and getting things working in things like this real like grapevine. So as an interesting trivia note, this is from my colleague Francisco at CMU, but this was taken at the Cornell Cooperative Extension Program in not in Ithaca, but in theory. So yeah, there's a lot of manipulation challenges, like reasoning about the type of deformability of trees and branches, contact and resistance. We do have a simulator where we developed this Isaac Chin simulator, and we trained reinforcement learning policy to try to manipulate models of trees that we developed. So this is not meant to be the final thing. It's meant to be debug and test. So yeah, and generally speaking, there's a lot of interesting future work directions that I want to get to, and we can think of them in terms of what is the application, but there's also underlying themes involved, like using about tools, mixtures, and layers. These concepts, I feel like if we can address them, they can be more general and apply to different settings. So, but yeah, that's the theme that I hope to pitch for you to work on in the next few years. And yeah, it's very exciting to be in this field and to see what we can make robots achieve. Yeah, and with that, if the lag is okay, with that, I'd like to thank my colleagues. Some of them are shown here, and yeah, I guess that's it for me. And I know I'm out of time, but I'm happy to take more questions if there's any.
Just so you know, so Daniel has a meeting immediately after this, so maybe we have time for 2 questions. That's it.
Yeah.
I wanted to ask, how does the transformation, SVD transformation, happen in test time?
What happens in testing?
SVD transformation.
What kind of transformation?
SVD.
Oh, the singular value decomposition. Well, that's part of the method.
Okay.
Like it's something that always going to be there for running tool.
Okay.
So it's like it's literally it's a fundamental layer in the gap.
So, like, what inputs does it require? I'm asking that.
Oh, the input is a segmented point cloud. It goes through a point net plus plus, and then we get an output that consists of 4 vectors. So for every single input point on the tool, we have a 3D vector. And those combinations of those things are the input. Because with these vectors, you can get a point cloud before and after. So yeah, more broadly, just think of it as 2 point clouds that are like almost aligned with each other. And SVD will find the transformation that best aligns them.
So for all possible input point clouds, the transformation is the same.
Yeah. No, it depends on the input.
Yeah.
Like if you have 2 point clouds that are almost perfectly aligned, SVD will tell you that the pose has like no translation and no rotation. But if the transformations are like rotated, SDD should tell you that to align them, you can apply this transformation.
Okay. Yes, there is a raised hand remote. Travers, you can unmute yourself and just ask.
Great, thanks so much. Great talk. I just had one question, sort of as it sounds like you have two main action representations. One is the next action at the current state, and the other you mentioned for some of your more dynamic tasks, planning long into the future with like parabolic trajectories. And I wondered if you could just give some brief like thoughts on where you see it, where your future work of going, whether it's more toward in this state, here's my one next action versus here's my long-term trajectory, or does it depend on the what task you're doing?
Yeah, so I guess just to be clear, are you asking like what like what are the action representations that we need for like short-term versus long-term action sequences, and if it depends on the task, which does. I mean, everything will depend on what task we have.
Got it, 'cause
I think you're talking about the dynamic manipulation tasks, like because like these tasks are very dynamic, but they're also in some sense like there's a dynamic action and then there's a settling state. So these are like more short-term dynamic action. So in that case, like it wasn't an issue with we should reduce the action representation to being like a parabola, then we follow that. Does that answer your like?
I think so. Yeah, I guess just to if I can follow up really quickly. So for the scooping motion, could you parameterize that also as a parabola and then just like roll it out and wait until it's over to see did it succeed or not? Or is that sort of the downside is you're not getting the feedback you could get from the system?
Yeah. So you can actually do a parabolic scooping motion. The issue is like in more complex environments, we would probably have like a lot of different items in whatever liquid mixture we have. So there might be feedback needed in terms of, if we scoop something, we adjusted the physics, we've adjusted the state of everything because liquid and a solid and everything interacting with each other in a solid way. So for more complex scooping, I feel like you need some more feedback, and a single parabola motion might not give you that.
That's awesome. Thank you so much.
And then Claire, last question.
Okay. So just about ToolFlow, I'm curious to hear what you think about how it works with like egocentric camera point of view. So like if the camera is on, the tool that it's manipulating, because it seems like it should be more robust than the kind of baseline method you were talking about, but maybe there's more things to consider.
Yeah. So as a quick backstory, this is related to the notion like where's the center of rotation that we consider of the tool, and it's the flow vectors are in like a roll space or the camera frame. So all these considerations do matter. They matter a lot. I didn't have time to cover it, but it does matter based on if you use an egocentric frame as a frame of reference versus the roll frame. In our case, I would say in general it matters. In the example that we covered, I normalized the coordinate frame so that everything is expressed in the roll frame, but you could do it with respect to everything in like the end effector frame or different frames. Yeah, the choice will play an important role.
Cool. Let's thank Daniel and Susan.